So everything is good?
Yeah,
okay.
Okay.
Dear colleagues, hello. My presentation will be about the nanostructures research using nuclear magnetic resonance of helium-3. Here on the slide, you can see the other group. It's Gleb Dolgorukov, Alexander Klachkov, Ekaterina Kondratyeva, Vyacheslav Kuzmin, Kayum Safiulin, Andrei Stanislavos, and Murat Tagirov. The main part of the work was done in Kazan Federal University. So on the next slide, you can see agenda of my talk. I will start from the synthesis of rare earth fluoride nanoparticles, say a few words about why it's interesting, and a few words about the synthesis and the structure and size modification. And after I will talk about X-ray diffraction, transmission electronic microscopy, and nuclear magnetic resonance of other synthesized nanoparticles. After a few words about helium-3, what is it and why experiments with helium-3 are interesting. After other NMR experimental setup, and the main part of my presentation, it's helium-3 in contact with other synthesized nanoparticles. So let's start. Here you can see the structures that we can synthesize in other laboratory. It's lanthanum fluoride-free nanoparticles. Also, we can dope it by gadolinium, for example, praseodymium fluoride-free nanoparticles, dysprosium fluoride-free, and terbium fluoride-free nanoparticles. Usually, we use the colloidal chemistry, and after they make a modification, it's size by autoclave or by microwave modification. Typical size are from 5 to 200 nanometer, and also usually we used experiments with a clean surface, but there is some experience of the coated surface of other nanoparticles. The main application with nanoparticles, it's laser technology, substances for targeted drug delivery, and also dysprosium fluoride-free and terbium fluoride-free nanoparticles. It's a perspective base for the high field MRI contrast agents. So we start from the typical synthesis in autoclave. Here on the slide, you can see the synthesis of lanthanum fluoride-free nanoparticles. We use a colloidal chemistry, starts from the lanthanum fluoride. They dissolved it in a deionized water. The second solution, it's a sodium fluoride in a deionized water, and after reaction, they have the lanthanum fluoride-free and sodium chloride. So this is, you can see the colloidal solution. In this solution, lanthanum fluoride-free, it's non-water soluble, and other parts are water soluble. And they put this solution to the autoclave for the different temperatures. The sample one, we don't put to the autoclave, and the next samples, it's for 140 degrees, 160 degrees, and 180 degrees for 24 hours in autoclave. So after they make XRD analysis, and here you can see XRD analysis of other nanoparticles, and here's the simulation spectra of XRD for lanthanum fluoride-free nanoparticles. So you can see that the structure of lanthanum fluoride-free and the peaks are narrow, and here you can see the data from transmission electronic microscopy. You can see the size of other nanoparticles, and also you can see that there is some clusters inside other particles, and this is a cluster of the water. And of course, they make the particle size distributions for every sample, and you can see here example for 160 degrees, and here the size dependence from the temperature. So you can see that the temperature effect on the size of other nanoparticles, and size became more bigger with temperature increasing. So on this slide, you can see the typical synthesis of nanoparticles with microwave radiation. Here's for praseodymium fluoride-free nanoparticles. We start from the praseodymium oxide, put it in a nitric acid, and after reaction has a praseodymium nitrate and water. And after in this solution, they add sodium fluoride, and after reaction has a praseodymium fluoride-free and sodium nitrite. So in this solution, non-water soluble, it's just a praseodymium fluoride-free. And after they put this solution to the microwave oven for the different time, so the sample 1 without microwave radiation, sample 2 for 20 minutes, after 40 minutes, 1 hour, and 7 hours. And after the product is collected by centrifugation and washed several times using distillated water. And here on the slides, you can see the colloidal solution of other praseodymium fluoride-free nanoparticles. After they make the XRD analysis of other nanoparticles, and you can see the peak and arrow, and we can say that this is a praseodymium fluoride-free structure, and there is no different XRD data for different samples for different times in a microwave oven. So here you can see the pictures of other nanoparticles. This is a sample 1 without microwave radiation. You can see that it has a polycrystalline structure, but just after 20 minutes in microwave radiation, the structure becomes more monocrystal, more ideal, and there is some cluster inside of nanoparticles, and they make the particle size distribution for every samples, and you can see here the dependence of the size on the time of hydrothermal reaction, and you can see that the size becomes more bigger after just 20 minutes, and after it's also about 30 nanometers. So after they make the NMR experiments, here you can see a mass spectra of praseodymium in other praseodymium fluoride-free nanoparticles. Here the red dots, it's for micro-size samples. Sample 2, it's 20 nanometers. It's 20 minutes in a microwave. You can see that the spectra becomes more wider, and black dots, it's sample 5, it's 7 hours in a microwave. You can see that the spectra looks like for micro-sized praseodymium fluoride-free, and we can say that there is a restructuring of the other samples by the microwave radiation, and also we can see it by the relaxation times. Here you can see the T1 times for praseodymium and also for fluoride. Depends on the time of hydrothermal reaction, and you can see that there is a rearrangement of the crystal structure, and the particle structure becomes more single crystal, becomes more like a single crystal. And also after the 7 hours, you can see that there is a big cavities inside in other nanoparticles, and we showed that this is water. So they make the experiments with the liquid nitrogen, and after nitrogen, you can see that the particles are destroyed, and also they make the macroporimetry for these samples, and we show that inside there is a water, and also they can modify the synthesis of our nanostructures, and for example, they put the heavy water inside other nanoparticles. So what is the helium-3 and why? And interesting, the difference of the helium-3 and helium-4 there is here. The main difference that there is a nucleon spin of the helium-3, and it's a fermions. So the helium-3 is lighter than the helium-4, and for helium-3 now the direct Bose condensation only by the Cooper pairing forming, and the helium-3 has a third largest magnetic moment, so it's a excellent NMR probe. And some more advantages of the helium-3, it has a small size, so the great permeability, low temperatures, and large magnetic moment, so it has a good NMR signal, and they can make the direct observation of wall relaxation. Helium-3 has a long intrinsic T1 times, so extremely effective wall relaxation and highly effective spin mass diffusion. The main application of helium-3 is the fundamental physics, surface science, material science, medicine for MRI of the human lengths, and of course helium-3 is a fuel of future. And here you can see other NMR setup. We have a typical temperature range from 1.5 to 4.2 Kelvin. Magnetic fields up to 800 millitesla. So here you can see the surface of other nanoparticles. For example, for lanthanum fluoride 3, here is a helium-3, and they can vary amount of the helium-3 in experimental cell and make experiments with just adsorb layer of helium-3, with a gas phase, and with a liquid helium-3, and also they can replating helium-4 or, for example, the nitrogen, and what is the distance from the helium-3 to the sample. So here is other nanoparticles. It's lanthanum fluoride 3 nanoparticles. This is a diamagnetic nanoparticles, typical diameter from 20 to 30 nanometers, and shape approximately spherical. Praseodymium fluoride 3 nanoparticles, it's a one-flag paramagnet. Here you can see the typical diameter and shape. And dysprosium fluoride 3 nanoparticles, it has a interesting transition from the paramagnetic to ferromagnetic states at 2.55 Kelvin. It was interesting to see what will be with helium-3 at the with phase transitions. So we start from the lanthanum fluoride 3. You can see here the T1 and T2 versus the magnetic field. You can see it for adsorb layer, gas phase, and also for liquid helium-3. And T1 and T2 dependencies of relaxation times place in favor of the mechanism of adsorbed helium-3. It's this mechanism was proposed by Kazan. Here you can see the T1 and T2 time. It's T1 T2 time on the surface in adsorb layer. This is all amount of helium-3, and this is a helium-3 on the surface. The praseodymium fluoride 3 with helium-3 system is interesting because of the possibility using the magnetic coupling between with two spin system, and it could be used for dynamic nuclear polarization of helium-3. So the one-flag paramagnet are known to have a high anisotropy of effective nuclear germagnetic ratio, and as a result, it's interesting to study the direct interaction between the magnetic moments with the equal amplitude of liquid helium if with the solid substrate. So here you can see the structure of praseodymium fluoride 3 and anisotropy of the germagnetic ratio and the germagnetic ratios for the helium-3. And here you can see the frequencies of transition between the nuclear energy levels of praseodymium. And here you can see that there is a cross area with the helium-3. So here the experiment. And for nano-sized particles, we know that should be the relaxation mechanism from the adsorb film. And the second mechanism, it could be because it's a one-flag paramagnet. There is a huge magnetic field in homogeneity, and could be relaxation in homogeneity of magnetic fields in space between the other nanoparticles. So the model that there is a two mechanism, first from adsorb layer, and it works at the low magnetic fields, and second in the magnetic fields and homogeneity. This mechanism was proposed by Professor Fatkulin, and it will be worked on the high magnetic field. And here you can see that we can approximate other experimental data for adsorbed helium-free gas phases and liquid helium-free by this two mechanism. And approximation is very good for this model, but we want to compare it with the lanthanum fluoride-free nanoparticles because the first mechanism from adsorb layer, it should be it should be the same for praseodymium fluoride-free nanoparticles and for lanthanum fluoride-free nanoparticles. And from other experimental data, we can minus with high field mechanism and compare data for praseodymium and for lanthanum. So here you can see that there is a difference in this mechanism for lanthanum and for praseodymium, and it may be that there is a one more mechanism of relaxation and with system, and it could be additional mechanism of the cross relaxation mechanism between the helium-free and praseodymium. The red line, which is a possibility of this cross relaxation. So also you can see that in the system for the sample 1 and sample 2, there is a difference in relaxation rates, and the relaxation rates in contact with the sample 2 is less than in contact with the sample 1, which is correlated with the size of nanoparticles. For sample 1, it's 20 nanometers. For sample 2, it's 30 nanometers. So we can see the size effect in this system, and also they make the computer calculation for the motion of helium-free in this system. Here you can see that the frequency fluctuation of the magnetic field differs by the factor 1.5, that it's like the size of these particles. So we can see the size effects by helium-free. And the last nanoparticles, it's dysprosium fluoride-free, and interesting that there is a transition from paramagnetic to ferromagnetic states at 2.55 Kelvin, and it is interesting to investigation of Curie temperature versus the size of nanoparticles, and also there is just one work of the spin kinetics of helium-free near with TC. So here you can see the magnetic susceptibility to the single crystal of dysprosium fluoride-free, and here you can see that there is a transition at 2.55 kelvins, but for the nanoparticles with size 5 nanometers and also 20 nanometers, there is no phase transition. So we start such experiments from the micro-size sample, and for micro-size sample in the temperature dependence of magnetic susceptibility, you can see that there is a phase transition near 5.55 Kelvin, and we prepare the mixture of the dysprosium fluoride-free and lanthanum fluoride-free micro-sized particles because there is no signal with just dysprosium fluoride free particles.
Well,
so here you can see.
Unfortunately, we have no time. Could you say that conclusions?
Okay, so just 1 minute. And also you can see here that we we saw the phase transition in this system at near 2.55 Kelvin. So also we try make it with nanoparticles, but for nanoparticles we couldn't see any anomalies of spin kinetics of helium-3 in contact with nanoparticles. And after we prepare the nanoparticles, these in a big size range, and here you can see for magnetic susceptibility for different sizes, you can see that if the particle size decreases, the TC shifts to the lower temperatures. So this is the final slide of my presentations. Thank you for your attention. Here's a part of other group. Please, questions.
We have time for very short question. One very short question, please, colleagues.
Well, if I may, just a very short question. Okay.
Yeah.
Yes.
Okay.
Yes, please.
Hi, Egor. My short question is as follows: how long does helium-3 atom stays on the surface of a nanoparticle, and how do you know it?
So if we make the adsorb layer, or just only amount for adsorb layer for other nanoparticles, it will be all time on this adsorb layer, just only there. And after, if we will put more atoms of helium-3, we can make the phase, we can make the helium-3 in a gas phase, and the gas phase could change the atoms from in gas phase and in adsorb layer. So, but in adsorb layer, it will be all time of experiment.
How do you know it? That it doesn't jump between particle and particle?
From particle to particle?
For example, yeah. But why do you think that it stays all the time on the surface of a nanoparticle?
No. I think that it could be jumped from one nanoparticle to another nanoparticle. It could be.
Sorry, may I ask a small question? In general, Olga Lapina, in general, NMR should be very similar to helium NMR. What is the difference, and why you choose the helium?
We choose helium because there is no helium in other nanoparticles. So if we see the signal, it will be from helium that they put in other experimental cell. And also helium-3 has a very good NMR signal, large magnetic moment, and also we can vary the amount of helium-3 in other experimental setup and make experiments with liquid helium and also the gas phase. So they can make a lot of different experiments.
Okay, I understand this, but why not xenon NMR?
Okay, no, it could be, but it will be different temperature ranges. And also it could make some experiments with the xenon, but it's different temperatures, so will be the different diffusions. So, but it could be done.
Okay, thank you very much. And
Sorry,
Ashwin,
but I have one remark.
you're welcome.
Excuse me. You use sometimes the notion for magnetic field B sub 0 and H sub 0. Is this misprint, or you use different denotions with certain meaning?
No, it's should be just be in all data.
But sometimes we use H sub 0.
Yes. So it should be in all my data. Yes.
It was misprint. Yes.
Yes. Yes. It's misprint.
Thank you.